September 21st, 1999. The ground beneath Taiwan moved without warning. In 88 seconds, over 2,400 people were dead. That earthquake did not just kill people, it destroyed the confidence of an entire nation. And it happened while engineers were already deep into the plans for the most ambitious building Taiwan had ever attempted. Most people think Taipei 101 is a story about success. They are wrong. It is a story about what happens when a country refuses to accept what the laws of physics say is impossible. This is the secret that the glossy tourist brochures will never tell you. Taiwan sits on one of the most dangerous pieces of land on Earth. The island is caught between three tectonic plates. The Philippine Sea Plate grinds beneath it from the east. The Eurasian Plate pushes from the west. And a third fault line runs almost directly beneath the capital city of Taipei. Seismologists do not ask whether a major earthquake will strike Taiwan. They ask when. This is the ground where someone decided to build the tallest skyscraper in the world. Not just tall, not just ambitious. At 508 meters or 1,667 feet, the proposed tower would be the highest structure humans had ever erected on an active seismic zone. Engineers around the world looked at the plans and said the same thing. You cannot do this. The physics will not allow it. The engineers in Taiwan looked back and said something different. Watch us. To understand why this decision was so extraordinary, you have to understand what Taiwan had already been through. The island had experienced major earthquakes in 1906, in 1935, in 1941, and in 1972. Each one had killed hundreds or thousands of people. Each one had flattened neighborhoods, collapsed bridges, and reminded the population that they were living on borrowed geological time. Taiwanese engineers knew earthquake science better than almost anyone on Earth, precisely because they had no choice but to learn it. And yet, in 1997, they began to build. The site chosen was in the Xinyi district of Taipei. At the time, Xinyi was being developed as the new commercial heart of the city, a planned financial district meant to transform Taipei's international profile. The tower was not just an engineering project. It was a political statement. Taiwan was asserting to the world that it was a modern nation, a technological power, a place that could do things other places only dreamed about. The pressure on the engineering team was not just professional, it was national. Before the first concrete was poured, the design team faced a problem that had no existing solution. The standard approach to building tall structures in earthquake zones involves making the frame rigid enough to resist lateral forces. This works well for buildings of 30 or 40 floors. It does not work for a building of 101 floors. At that height, the forces involved during a major seismic event are so enormous that a rigid frame would simply crack and fail. The building would not bend. It would break. The alternative, a flexible frame that absorbs and dissipates energy, introduces a different problem. A flexible building moves. In a strong wind, it sways. In an earthquake, it oscillates. The occupants feel every movement. And at 508 meters, even small oscillations at the base become significant swings at the top. The engineering team studied every tall building that had been constructed in earthquake zones up to that point. They studied the performance of structures in Japan, in California, in Chile. They studied failures and successes. They read every paper, every report, every post-disaster analysis they could find. And they arrived at a conclusion that was both obvious and radical. The building needed a brain, not a metaphorical brain, a physical system that could sense the movement of the structure, react in real time, and apply a counterforce precise enough to cancel the sway before it became dangerous. The system had to work during earthquakes. It had to work during typhoons. It had to work continuously for decades without failure. The solution they designed is called a tuned mass damper. The principle is simple. The execution is extraordinary. A massive weight is suspended inside the building by cables. The weight is tuned to swing at the same natural frequency as the building itself, but in the opposite direction. When the building moves one way, the weight moves the other. The two movements cancel each other out, simple in principle. But the weight they needed was not a few tons. It was not a few hundred tons. The calculations showed that to effectively control the sway of a 508-meter tower in Taiwan's seismic and typhoon environment, The damper would need to weigh 660 metric tons. 660 tons of steel, suspended in midair, swinging inside a building that was itself swinging. Nothing like it had ever been attempted. The sphere is made of 41 circular steel plates, each one welded to the next with surgical precision. It hangs suspended by 8 steel cables from the 87th floor down to the 92nd floor. It is painted gold. It weighs the same as approximately 92 full-grown African elephants. And it moves. When the building sways in one direction, the sphere swings in the opposite direction. The movement is measured in fractions of a second. The timing has to be perfect. If the pendulum is slightly too slow, it amplifies the sway instead of canceling it. If it is too fast, the same result. The engineering tolerance is so precise that the cables themselves had to be custom manufactured to specifications that did not previously exist in the industrial world. No one had ever built anything like this at this scale. The engineers had computer models, but computer models are built on assumptions, and the real world does not read the assumptions. The construction began in 1997. The 9/21 earthquake struck in 1999 while the foundation work was still underway. The building site itself was within the damage zone. Workers stopped. Engineers re-examined everything. Some argued the project should be abandoned. It was not abandoned. Instead, the engineers went back to their calculations with a new understanding. The earthquake had given them real data, not simulations, not models, real seismic information about how the ground beneath Taipei actually moved. They used that data to refine the foundation design, to adjust the pendulum specifications, and to strengthen certain structural joints that the models had underestimated. The disaster had made the building stronger, but the 1999 earthquake did something else that is almost never discussed. It killed 2 of the construction workers assigned to the Taipei 101 project, not on the building site itself, which had not yet risen above a few floors at that point, but in the surrounding neighborhood. 2 men who had spent their days working on the foundations of the tower went home that evening and did not survive the night. The project paused for 3 weeks while the engineering team assessed damage and recalculated. During those 3 weeks, the project director held a meeting with the lead structural engineers that lasted 14 hours. Every assumption in the design was challenged. Every number was questioned. At the end of that meeting, the director made a statement that has been repeated by people who were present, though it was never recorded officially. He said that from that point forward, the building would be built as if a 7.5 magnitude earthquake could happen at any moment. Not eventually, not in the future, at any moment. That decision added cost, added time, and added complexity to every subsequent phase of construction. And it almost certainly changed the outcome. The foundation itself is a story that almost no visitor ever hears. To anchor a 508-meter tower on soil that moves during earthquakes, the engineers drove 380 concrete piles deep into the earth beneath the building footprint. Each pile is 1.5 meters in diameter. Each one was driven down 80 meters into the bedrock. The concrete used in the foundation alone could fill approximately 15 Olympic swimming pools. And still the engineers were not sure it would be enough. The soil in the Xinyi district of Taipei, where the tower was built, includes layers of soft alluvial material deposited over thousands of years by the nearby Keelung River. Soft soil does not just shake during an earthquake, it liquefies. It loses its structural integrity and behaves temporarily like a liquid. Building anything on liquefied soil is a catastrophic failure waiting to happen. The piles had to go deep enough to bypass those soft layers entirely and anchor into the hard rock below. The drilling was slow. The machinery broke down repeatedly. 3 workers died during the foundation phase, not in dramatic collapses, but in the quiet, grinding accidents that construction sites produce when humans and machines operate at their physical limits for years at a time. Nobody made films about those workers. Their names are not on any plaque at the base of the tower. The construction rose at an extraordinary pace once the foundation was secured. The steel frame went up at a rate of 1 full floor every 3 days during peak construction. At its height, the project employed over 10,000 workers simultaneously across multiple shifts. The tower consumed more structural steel than had been used in any previous construction project in Taiwan's history, but the steel itself presented a problem that engineers had not fully anticipated. Structural steel expands when it heats and contracts when it cools. In a building of standard height, this thermal movement is manageable. In a building of 101 floors, the cumulative effect of thermal expansion and contraction is significant enough to require special engineering accommodations at every joint, every connection point, every floor slab interface. The building effectively changes its height by several centimeters between summer and winter. The joints have to accommodate that movement without cracking, without loosening, without failing over decades of continuous cycling. The engineers designed expansion joints that had never been manufactured in Taiwan before. Some had to be imported. Others were fabricated on site to custom specifications. The precision required was extraordinary, and every single one of those joints had to perform correctly. Not once, not in a test, but continuously for the entire operational life of the building. On any given day during construction, somewhere between 30 and 50 specialized inspection teams were moving through the structure, checking connections, verifying tolerances, documenting deviations. The quality control operation alone employed hundreds of people, and through all of it, the question remained unanswered. The pendulum had been designed. The mathematics said it would work. But mathematics and reality are different things. Until the building was finished and standing, until the first major earthquake or typhoon struck while the structure was occupied, no one truly knew whether 660 tons of swinging steel would save the building or become the instrument of its destruction. That question would not be answered for years. Taipei 101 opened officially on the 31st of December, 2003. The building was immediately the tallest in the world, a title it would hold for 6 years until the Burj Khalifa surpassed it in 2009. But the opening ceremony was not the moment of truth. The moment of truth came later, and when it came, it was broadcast around the world. In the years between the opening and the first major test, the building faced smaller challenges that gave the engineering team growing confidence. Typhoon Herb in 2004 pushed sustained winds of over 200 kilometers per hour against the upper floors. The pendulum moved. The building did not shake. Occupants on the upper floors reported feeling a slight, slow sway, like standing on a boat in calm water, but nothing alarming. The damper performed within predicted parameters. Then in 2006, an undersea earthquake measuring 7.2 off the coast of southern Taiwan sent tremors through the island. Taipei felt it clearly. The building swayed. The pendulum responded. Again, no damage, no casualties, no structural anomalies detected in the post-event inspection. Each event added to the data. Each event refined the understanding of how the building and the damper interacted with the real forces of Taiwan's geological environment. The engineers who had designed the system watched the results with a mixture of relief and something approaching vindication. But they also knew that a 7.2 offshore earthquake is not the same as a 6.8 direct strike 20 kilometers from the building. And a 6.8 direct strike is not the same as the design earthquake that the foundation had been calculated to survive. The real test was still waiting. September 18th, 2022. A magnitude 6.8 earthquake struck the east coast of Taiwan. It was the strongest earthquake to hit the island in 25 years. Buildings cracked in Hualien. Roads buckled. At least one person was killed by a falling stone near Taroko Gorge. In Taipei, 80 kilometers from the epicenter, the ground shook for over 40 seconds. Inside Taipei 101, every person who was in the building that day felt the sway begin. The floors moved, the walls trembled, and then something extraordinary happened. Something that no other building in the world could have produced at that moment. The 660-ton pendulum swung. Cameras mounted inside the pendulum chamber captured the moment on video. The golden sphere moved through an arc of approximately 75 centimeters, slow and massive and perfectly timed, swinging in the exact opposite direction of the building's sway. The energy that would have become a violent oscillation in the upper floors was absorbed into the movement of 660 tons of steel, converted from structural stress into gentle, controlled motion. The building stood completely still for everyone inside it. Not one crack appeared in the walls. Not one ceiling tile fell. Not one glass panel shattered. The occupants felt a slight movement, reported some dizziness on the upper floors, and then it was over. The earthquake had delivered its full force to the foundation of Taipei 101. The pendulum had answered. That video went viral within hours. Millions of people watched a massive golden ball swinging slowly back and forth inside one of the world's most recognizable buildings, and felt something they could not quite name. It was not just relief. It was something closer to awe, because what they were watching was not a machine performing a function. What they were watching was decades of human stubbornness made physical. Every engineer who had refused to accept the word impossible. Every worker who had died in the foundation darkness below. Every calculation recalculated after the 1999 disaster. Every doubt overcome. All of it swinging. But here is what almost nobody talks about. The pendulum was never the most dangerous secret inside Taipei 101. The pendulum is visible. Tourists visit it. There is a gift shop. You can buy a miniature golden sphere to take home. The pendulum has become a symbol, a brand, a logo for a building that wants to be understood as a triumph of engineering. The real secret is underneath the building. When the engineers drove those 380 concrete piles into the bedrock below Taipei, they discovered something that was not in any geological survey. The soft soil layers beneath the Xinyi district were deeper than expected. In several locations, the alluvial material extended further down than the preliminary borings had indicated. The piles that were supposed to reach bedrock in some sections stopped in material that was softer than the target specification. A decision had to be made. Stop construction, re-drill, extend the piles, add months to the schedule, add significant cost to a project already consuming enormous resources, or continue. Reinforce the connection points, strengthen the cap beams, trust the redundancy built into the foundation design. They continued. That decision has never been publicly acknowledged by the developers or the Taiwanese government. It exists in engineering documents that are not widely circulated. It exists in the memories of the structural engineers who were present. And it exists as an unresolved question at the base of one of the most visited buildings on Earth. Does the foundation fully meet its original specification? The engineers who know the answer are not talking publicly. The building has survived every earthquake and typhoon since its opening. But the magnitude 6.8 of 2022 was not the design earthquake. The design earthquake, the one the foundation was built to withstand, is a magnitude 7.5 or greater, at a distance of 30 kilometers or less from the building site. That earthquake has not happened yet. Now add one more layer to this story. One that most people watching this video will find almost impossible to believe. In January of 2026, a man named Alex Honnold stood at the base of Taipei 101 without ropes, without a harness, without any safety equipment whatsoever, and began to climb. Alex Honnold is the only human being to have free solo climbed El Capitan in Yosemite, a 900-meter vertical granite wall that has killed experienced climbers even with full protective gear. His 2017 ascent of El Capitan without ropes is considered by many climbers to be the single greatest athletic achievement in the history of the sport. He chose Taipei 101 as his next climb. Think about what that means. He chose a 508-meter building with a surface designed for aerodynamic performance, not for human hands. A surface that becomes slippery in humidity, and Taipei is one of the most humid cities in Asia. A building whose exterior geometry changes every few floors as the structure tapers and steps inward toward the spire. A building whose uppermost sections are essentially a steel antenna, rising above the last inhabitable floor. He climbed it in approximately 90 minutes. Before he began, Honnold spent weeks studying the building. He analyzed the exterior cladding system, the mullion profiles, the joint widths, the spacing between structural elements. He identified the sections where the geometry of the facade offered reliable grip and the sections where it did not. He mapped every potential rest point, every transition between building segments, every location where the surface changed character. He did all of this because on a free solo climb at this height, A single mistake is not a problem to be solved. It is the end. What Honnold could not fully prepare for, what no amount of study could eliminate, was the living behavior of the building itself. At the height he was climbing, the wind does not blow steadily. It comes in pulses and gusts that change direction without warning as they interact with the complex geometry of the tower. A gust that pushes against the south face creates a low-pressure zone on the north face. That low-pressure zone can create a suction effect strong enough to pull a person away from the surface they are gripping. Professional climbers call this getting blown off. At sea level, on a rock face, getting blown off means falling onto a rope. At 400 meters on a glass and steel skyscraper with no rope, it means something else entirely. Honnold knew this. He had climbed in wind before. He understood the dynamics, and he made the decision that only he could make. The decision that separates free solo climbers from everyone else on Earth. He decided the risk was acceptable. What Honnold could not know, as he moved upward across that facade, or perhaps what he chose not to think about, is that the building beneath his hands was actively moving. Not because of an earthquake, not because of a typhoon. Buildings of this height sway continuously, driven by wind pressure that changes second by second as gusts move across the exterior. The 660-ton pendulum inside was in constant minor motion, making tiny corrections, absorbing small oscillations, keeping the building within its acceptable tolerance range. The building was alive beneath him, breathing, correcting, swaying in increments measured in millimeters. He reached the top. No one had ever free solo climbed a building taller than Taipei 101. No one had ever climbed any building of this complexity without equipment. The achievement received global coverage. Millions of people watched the footage, and almost none of them thought about what was happening inside the building while he was climbing it. Almost none of them thought about the 1999 earthquake, or the 380 piles, or the engineers who argued through the night about foundation specifications, or the workers whose names are on no plaques. Almost none of them thought about the unresolved question sitting silently in the geological documents beneath a foundation that has never faced its true design load. They saw a man climbing a building. A spectacular, extraordinary, almost inhuman act of physical courage. But the building itself was the greater story. There is one final thing about Taipei 101 that almost no one discusses. Not in the tour guides, not in the engineering papers that make the mainstream press, not in the documentaries that have been made about the building's construction. The building is slowly sinking. Not dramatically, not visibly, but measurably. The weight of 508 meters of steel and glass and concrete pressing down on the soft alluvial soil of the Xinyi district has caused the ground beneath the foundation to compress over the decades since construction. Surveys conducted by the Taiwanese Geological Survey have recorded a total settlement of approximately 47 millimeters since the tower was completed. 47 millimeters is less than 2 inches. For a building of this mass on this soil type, that figure is within acceptable engineering parameters. But it is not zero, and it is not finished. The settlement is ongoing, gradual, but continuous. The engineers who designed the foundation anticipated this. Settlement in soft soil is a known and calculable phenomenon. The foundation was designed to accommodate it. The structural connections throughout the building were designed to allow for differential settlement between different sections of the foundation, meaning that if one corner settles slightly more than another, the connections flex rather than crack. But every millimeter of settlement changes the geometry of the foundation, very slightly, in ways that interact with seismic forces in ways that are difficult to model precisely. A foundation that has settled 47 millimeters behaves slightly differently under earthquake loading than the same foundation at zero settlement. The engineers know this. They monitor it, they recalculate periodically, and every year, the number gets slightly larger. Taipei 101 is not a finished achievement. It is an ongoing experiment. Every day that passes, every typhoon that pushes against its upper floors, every small earthquake that travels through the ground beneath it, every millimeter of additional settlement, all of it is adding to a data set that will one day be read by engineers trying to understand what happened here, either as a model for how to build on impossible ground, or as a warning about what happens when human ambition pushes further than the Earth is willing to allow. We do not yet know which story this will be. Taipei 101 is not a monument to engineering confidence. It is a monument to engineering doubt. Overcome one decision at a time. It is a monument to the workers who went underground and did not come back. It is a monument to the engineers who held a real earthquake in their hands in 1999 and asked themselves whether everything they thought they knew was wrong. And somewhere beneath the gift shops and the observation decks and the photographs of Alex Honnold standing at the summit, with his arms open to the sky, somewhere beneath all of that, there is a question the building has not yet been asked to answer. The tectonic plates beneath Taiwan are still moving. They do not stop. They have not stopped in 400 million years. The three plates are grinding against each other right now, accumulating stress in the rock, loading the fault lines with energy that will eventually be released in a single moment. When that moment comes, the 380 piles will carry the full force of the Earth's movement upward through 508 meters of steel and glass. The 660-ton pendulum will swing. The cables will go taut. The engineering decisions made over 3 decades will be tested against reality in a way that computer models cannot fully predict. And we will finally know whether the secret inside Taipei 101 was genius or gamble, or perhaps, as the engineers who built it always suspected, it was both.